Hello students, this is Mr. McAllen again, and today we're going to talk about graphing binomial functions but using transformation. We're also going to discuss end behavior and we're going to use the y-intercept. So let's first get the functions drawn correctly and then we'll discuss the other two aspects. So in the first function g of x, we're asked to graph g of x and we're going to use transformations. So the first thing we notice is the parent function is x cubed, so it's going to look like a cubic function. The function is move left 1 because of x plus 1. There's a vertical stretch by a factor of 4, so that means it's going to be vertically stretched 4 times. And when we go to plot it, we're going to take it used to have its origin, or its let's call it its center point or vertex at -1. I mean at 0, 0, but it's going to move to x equals -1. So we're going to go to -1, and that's where we're going to put its vertex. And there's a stretch factor as a factor of 4. So we should plot the y-intercept by just plugging in x equals 0 into the function. So when we do that, when x equals 0, we get, well here, let's make a little table just to help us out. So this will be x and this will be g of x. So when we plug in 0, we get 1. When we put in -1, we get 0. If we put in -2 into the function, we would get, again, when you put -2 and you get -1 cubed times 4, so you get -4. And I have to make a correction on the first point. The first point is not 0, 1. The first point, when you put 0 in, you get a value of 4. So here you can see that using the y-intercept and another point on the opposite side, we could see the symmetry of the function, or not the symmetry, but you can see the general shape. So it's a pretty well stretched cubic function. So that would be how we use the y-intercept to find out where the functions cross on the y-axis, and I used an extra point to make a better graph. Now remember, this is a sketch, and I do want to describe its end behavior. So what's happening at the ends of the function? So just to make things clear about what the ends mean, this over here, as the x value goes to infinity, we're on the right end of the function, and as the x value heads to -infinity, we're on the left end of the function. So end behavior means what does the function look like at its ends? Where is it going? So what I'm going to say is I'm going to introduce a limit statement. So a limit basically will describe for us, LIM. There are two parts to a limit statement. There's the part which describes what's happening as x, where x is heading to. So in this case, x is heading to infinity. So as x heads to infinity, what does the y value head to? And as you can see here, the y value is heading off to infinity because it's going up and up and up on the blue function. So that's the end behavior on the right end. On the left end, let me change back to the blue ink. I have the limit as x goes to -infinity. Where is the function heading to? So as the function is heading to, as we're heading off to -infinity in the x, the function is heading down to -infinity in the y. So I would write here for my limit, let me just clean this up a little bit. I would say the limit of, now I'm just going to write g of x here in red. As x heads to infinity, -infinity, the function value heads to -infinity because it's going down and down and down. So that's how we describe end behavior using limits. So let's work on this next function. On the next function, just clean everything up here so we can concentrate. We have a parent function of x to the fourth. We have it moving right 2, 5 from looking at the transformations, and we have a flip over the x. So what we're going to do is we're going to move the vertex. We're going to go right 2. We're going to go up 5. So that's my vertex. I know the function will look like an upside down parabola because it's an even power function. It has that same general shape as any even powered function. Its vertex is moved to 2, 5. It's flipped upside down. So I just have to get the y-intercept value. So I'm going to plug in for x, and this is h of x. I hope that's h. Yep. So this is 0 I'm plugging in. And when I put 0 in for, to be on the y-axis, I'm going to have negative 2 raised to the 4th power with a negative outside, add 5 to it. So when I do that math, I'm going to get negative 16 plus 5. I'm going to be at negative 11, which tells me this is 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's where it's going to go through. So it's a pretty steep function. And so basically that's what the transformed monomial would look like. So now what I want to do is I want to describe end behavior. So again, as x goes to infinity, on the one side, because I have two ends to describe, I have a left end and a right end. My y value is heading to negative infinity. And as x goes to negative infinity, my function is heading also to negative infinity. So when I write out these limits, I would write out the limit LIM as x heads to infinity, h of x heads to the y value, heads to negative infinity. It's heading down and down and down. And on the other end, the limit as x heads to negative infinity, g of x heads to negative infinity as well. So these are my two end behavior statements that describe the graph I drew. Hope this video helps. This is the first part of 3 videos. So the next video we'll be talking about what happens when we add monomial functions and how to work with its graph. Look forward to hearing your comments. Take care.